Okay, this is my example for the force table, and I filled water in these bottles. I put 235 grams in here and measured it, and this one is going at 270 degrees, and I put 495 grams into this one, and this one here is going at 180 degrees. I'm not going to let them hang right now because it's not going to be stable. I need to have everything set up at once. And this one here, to show you how I measure this one here, so I'm going to determine how much mass it has, and I have to tear it in the vertical because that's how I'm going to hold it. So here we go at 0. And so now I'm going to tie this around here. And this kind of string here is going to hold on to the lid. This is actually my second or third take, and I noticed that this thick string later on for the experiment itself will not work. It's going to work just fine for determining the mass. But in fact, there it slips a little bit. 175 grams is what I have, so about 1.75 newtons. But if I tied it to my experiment here itself, it exerts too much friction, and so I don't. I use string that will have much less friction. Okay, and now it gets interesting. So here goes my first bottle at exactly 0 degrees. So this is the 175 grams mass, about 1.7 newtons. Here is the 235 grams, or about 2.3 newtons. And then, I left the spring scale over there. Thank you. Everything will start slipping on the pedal. Like every day. Okay, let's see what I get here. I have to make sure that everything is
horizontal tear.
Yeah. Oh yeah, I have to pull in this direction here to hold it. And then actually I just noticed something. I need to retie this one over here because the knot is slipping, so I only made one knot in there. So I guess you could keep taping. This is, after all, troubleshooting. So this is how you tie a knot, right? Yeah, that wasn't too bad. Okay. There we go. Okay, now I ran into a different kind of problem. My string on one side is too short, so I need to retape this one here pretty much in the X direction this way and in the Y direction this way. I actually don't have to use the middle of the table, but what I have to pay attention to is that these are aligned with the horizontal, the X, and this one here with the Y, and then this one here goes off perpendicular, and so do the other two. On this particular table that I choose, I actually have a groove in the middle which tells me the X direction. I tried to do this with pulleys and putting them on Play-Doh. I have these over here, but it turned out, well, it could have produced too much static friction there. So I'm just trying the beveled edges of this table here and see how this works out. And so now I'm ready to measure. So what you're seeing here, of course, is the kind of troubleshooting that you might have to do. And then, of course, I have to pull it in just the right direction, so apparently not in this direction, but somewhere over here. So I want to say I'm at 30 some degrees. 33 degrees is what I'm reading. That seems to be my best angle. Yeah, if I pull over here it's not going to work, so it has to be, yep, about 33 degrees. And I'm measuring approximately 3.7 newtons. So of course I'm measuring the force here. Over here I have masses, but they themselves are weights as well, so I have to eventually convert those to newtons. And I'm going to take my string here and a little bit more in the middle there, and yeah, that's what I got. 33 degrees, and what did I say, 3.7 newtons. And that's my example. I'm going to make example calculations with that, and then of course you're going to make your own measurements with the numbers given to you. Okay, thank you.
These are my example calculations for the lab on the force table. So let's get to the table on the paper that I actually set up my example. So this is, when you watch the video, is what I said, that's what I measured prior to actually doing the video. 495 grams at an angle of 180 degrees, 235 grams. I'm sorry, this keeps coming in there. 235 grams at an angle of 270 degrees, and then this is what I measured while I did the video, 175 grams at an angle of 0 degrees. So I'm going to calculate the force, that is the weight, once I have hung them on the strings and let them hang over the edges of the table. So it's going to be 495 grams divided by 1,000 to get it kilograms, and then times the acceleration due to gravity, which is 9.8. So that comes out to around it 4.9 newtons. Okay. And 235 divided by 1,000 times 9.8 comes out to 2.3 newtons. And I'm going to keep it here in two significant figures because, as you notice here in my grams, it's basically just two significant figures, with the last one being an estimate halfway between, in this case, 490 and 500. That's the best accuracy the spring scale can give me anyway. So that's why I keep my weights right here at two significant figures. And 175 times divided by 1,000 times 9.8 should come out to 1.7 newtons, and that's indeed correct. Okay, so these are the data that I have to work with, my example data. And I'm going to go here. There are four methods that I have to use: the graphical method, the applet, the trigonometric method, and the measured method. So let's see, I'm going to start out with the graphical method. It says, for each setup you need two drawings on each Cartesian graph paper. In the upper half, make a large enough drawing in the XY coordinate system and draw in the force vectors emanating from a single point. In the lower half, make a second drawing with the same vectors tip to tail. Pay attention to each vector keeps its length and direction. Measure the magnitude and the angle of the net force. I kind of skipped this one here. I use small ring. When you watch my video, you can see that instead of using a small ring, I actually just used a knot. I knotted the strings together. Okay, this is the graphical method. Okay, I'm going to choose a single point here with something. There we go. There, that could be the ring that I actually didn't use. And I'll put it here, say. And then I'm going to measure at, let's see, 180 degrees, which is to the left, 4.9 newtons. So 4.9 newtons would be this much. There we go. And there we go. Then I measured at 270 degrees, 235 grams. Uh, 2.3 newtons, that is. So 2.3 newtons. That looks like there. There. Okay. And then I measured at 0 degrees, 1.7 newtons. And that is my first drawing. So looking down at the table, one weight is pulling this direction, another one this way, another one this way, and then of course I have my counter force acting on it. Okay, the second drawing is you would draw these again, tip to tail, that is. And here what I'm going to do actually is I have the luxury that I can move these around, so what I'm going to do is I just copy them. Sorry that I'm a little lazy here. You would have to redraw them, but that's no big deal. Let's see. Oh, there it is. Okay. Okay, so I would grab one of the three, it actually doesn't matter which one of them, and put it down. Now I put another one, and I put it tip to tail. And it looks like I have to move this a little bit in the screen. And then I take the third one, and I move it tip to tail. And as I said, any kind of order would actually work. I could have started out with this one. I can show you. Oh, hold on, let me actually show you that this is the gap here. This is the net force from the original tail to the final tip. Kind of remember that's what it is. And if I turn these around some kind of other order, for example, I would start out with this one here, continue with this one, and end with this one. Notice that from the original tail to the final tip, it's again the same one that I just drew a moment ago, or that I pointed out a moment ago. Okay, the net force, therefore, I'm going to change the color on this one here, make it green. This here would be, therefore, the net force. In this direction, the entire assembly is pulling, and I kind of can see it with this large vector over here, that probably the whole assembly wants to take off in this direction here. Okay, this one here, I'm going to measure how much it is. And again, you would have to redraw them a second time yourself, but with these right angles, that's no problem at all. And on, I believe, one of the setups, you actually have to turn it a little bit. You have a different kind of angle because you go over a corner, and you would have to use actually a protractor to draw in that correct angle. Okay, anyway, I'm going to come up with, looks like what I drew here is 3.7 newtons. So 3.7 newtons at an angle of, and I have to turn my protractor around, angle of, let's see, this one, I'm going to read 30 plus another 5, looks like 35 degrees past the 180 degree mark, because I have to go from here all the way around, because this one is actually 0 degrees, that is 90 degrees, 180 degrees, 270 degrees, so this one is 35 degrees past 180 degrees, so it's 215 degrees with 3.7 newtons. So that's the graphical method, and this is what you would submit. Actually, I will write it down here. Okay, so that was 3.7 newtons. That looks a little small here. At 215 degrees. That looks a little better. There we go. Okay, so my result, therefore, for my example are the graphical method, 3.7 newtons at an angle of 215 degrees. Okay, the second method says the applet. An online applet or an online vector calculator compute the magnitude and the angle of the net force. Google vector addition applets and so on. So we go to this one here, and I'm just going to do this one and pull it up. So there it is, and that actually does the work for us. It will put all the vectors tip to tail. Still, I want you to make the drawings because that immerses you into actual doing it, and the understanding should be more clear when you actually have to do it yourself than simply just using this applet. And that's also a reason why I do both. Why I have you do both. Okay, let me see. Let me push this up a little bit more. Okay, on the applet. So I would have 2.3 newtons at an angle of 270 degrees. And I would have 4.9 newtons at an angle of 180 degrees. And notice what's happening. This applet here, unfortunately, cannot really make it to scale. So with, oops, I didn't mean to do that. With such small numbers, the vectors are way too tiny. So what I'm actually going to do instead is I'm going to multiply each number with 100 by 100. So I'm going to have 230 at an angle of 270 here. This looks almost like I'm using the grams. And then 490 at an angle of 180 degrees. And now it looks a whole lot nicer. That one's actually pretty long. And then I need a third vector, and that would be 170 at an angle of 0 degrees, and that one comes straight back. And that's yet another possibility how you can add these three vectors graphically in whichever order, and that's what I pointed out in my graphical method, that it doesn't matter in which order you put them. Okay, show the resultant. And that looks pretty much the same the way I just drew it. Notice that it measures here 3.9 newtons. Again, remember that I had to scale everything by a factor 100, so 3.9 newtons at an angle of 216 degrees. And that's what I'm going to write down here. So 3.9 newtons at an angle of 216 degrees. Looks pretty similar to the graphical one, and you would have to decide, which one of these two is actually more accurate. The one you draw yourself, or the one that you let the applet do. And you have to talk about that in the conclusion and perhaps in a post-lab question. Okay, trigonometric. If you're in a physics class that does not require trigonometry, leave this one out. If you are in a physics class that does require trigonometry, of course, you will do this one here. Okay, so here it would be. I didn't type the example in. I think I'll take a moment out here and we'll actually do that. Okay, here I've just done that. So, example. This would be force 1, which is 2.3 newtons, times the cosine of the angle of 270 degrees. I'm going to leave out the degree sign here. I'll put it in a moment. Plus 4.9 newtons times cosine of 180 degrees. And plus 1.7 newtons times the cosine of 0 degrees. Okay, now I'm going to put that one in and use a superscript on it. And, whoops, there we go. And here we go. That's in the x direction. For the y direction, I'm going to use the sine, of course. Sine. And there we go. Okay, and now I calculate. Okay, so here's the calculator. And it says, oh, first I'm going to see if I'm in degrees. I'm not, so I'm going to change this to from radians to degrees. And then it's going to be 2.3 times cosine 270 plus 4.9 times cosine 180. And I just noticed I forgot to close the parentheses, plus 1.7 times cosine of 0. Hit enter. That's the first one. The negative, of course, means that it points to the left. And then the y direction, all I have to do is just do exactly the same thing, except change the cosines to sines. Okay, and again the minus means that it points down, so minus 3.2 minus 2.3. Negative 3.2 newtons and negative 2.3 newtons. In order to figure out what the net force is, I have to use the Pythagorean, so I'm going to do the square root of negative 3.2 squared plus negative 2.3 squared, close parentheses for the square root, and I come up with 3.9 newtons. Of course, that's exactly the same number that the applet gave me. And for the angle, I'm going to do the inverse tangent of the y component over the x component, and I come up with that 36 degrees rounded, and of course I'm in the third quadrant, so 36 degrees plus 180 degrees is the 216 degrees. So this one comes out to 3.9 newtons, and this one comes out to 216 degrees. Let's see if my degree sign didn't work anymore when I paste it. Okay, so turns out that right here on this one, the trigonometric one is identical to the applet one. That's no surprise because the applet one, of course, is based on the trigonometric method, as you can imagine. And the last one here is actually what I measured. Well, from the video, you may remember I measured 3.7 newtons at an angle of 33 degrees. I believe that's what I said. So, comparing the numbers here, what I actually measured here is pretty close to what I determined trigonometrically or applet or the graphical method. The angle here, why is that different? 33 degrees, quite different from 215 or 216 degrees. Well, that's because this measured force here is the counter force to the net force being measured over here. Notice that for these here I wrote down the net force of these three weights that I have hanging over the strings, and this one here is the counter force. So it has to be in the opposite direction, and notice that 33 degrees would be opposite of 213 degrees, and that of course is relatively close to the others. And when you do your calculations, your results, you would have to comment on comparisons between these methods over here and what was actually measured, and perhaps in between here, and figure also out what kind of errors are involved in this experiment that puts the results a little bit different from perfect results. And that was my example for the force table.